Bennett, please, I think you can start. Thank you.
We can start? Okay. Just let me close the water bottle. Okay, so hi, everybody. I was told that you can see and hear me. Yeah, at first, thanks for having me here. Many greetings from my little quarantine island. Yeah, other than my former speakers, I have structured my presentation a little bit differently. So during my presentation, I will give 3 statements to open a following discussion about my further research, because I'm in my 3rd year as a PhD researcher at our university, and I'm starting to develop my topic, and I'm really happy to hear your feedback afterwards. So the title of my presentation is Wire Arc Additive Manufacturing, 3D Printing of Column Structures for Architectural Applications. And what I'm going to talk about is at first about the printing process itself, so wire arc additive manufacturing, then why columns are really nice to look at, and then how you can make, with a little bit brainstorming and everything, a really nice idea for a research topic, hopefully. Yeah, many people think 3D printing is quite easy. I mean, you all have had to challenge this problem. You can use a filament like PLA, you have a printer, common printer, and you have your model, press start, and then it runs. But sadly, that's not how it works for wire arc additive manufacturing. On the slide, you have, or you can get a little impression of our laboratory. And like Mr. Naboni said, yeah, that happens quite rarely that it looks that nice. About wire arc additive manufacturing, it's based on gas shielded metal arc welding, and it has a wire as the filler material. And this wire can be stainless steel, carbon steel, different alloys. So a lot of things you can work with. It also works layer by layer, material depositioning, and a huge benefit of W.AMCA is that it's the deposition rate is 30 to 40 times higher than, for example, powder-based additive manufacturing processes. And also, the investment costs are much lower compared to powder-based additive manufacturing again. On the slide, I have highlighted in black some critical parameters for the W.AMCA process itself. So you have, of course, the wire feed, you have the power supply, you have the robot you have to control, and then you have your input, the wire electrode, and also the shielding gas, which has a huge impact, and what I'm going to talk about a little bit in a moment. About the process itself, for me, it sounded a little bit like it's similar, also, of course, to Maren and also to Mr. Naboni, that we have a digital model at the beginning. So on the left side, you can see one, let's call it trophy or column structure, we have already printed. And to start this process, we needed our digital model with process and input parameters and material characteristics, which gives us our base model. I will just show you on this slide a little bit about the parameter setting, and here especially about the shielding gas. So what you can see here on the left axis, you can see it's a layer height. And on both sides of the black line, you have the results for the layer height for similar parameter settings, but just with different shield gases. On the left side, it's C18, which has a higher active gas percentage than the ferroline CX1, which has less CO2, also carbon dioxide, and also 1% of oxygen. What does it show to us? We have higher, or we can generate higher layers with C6X1 because the melting pool is, the temperature of the melting pool is lower, because of the lower percentage of active gas. And so it shows us that the shielding gas has a significant impact and makes it really interesting for research. But on the funny side is, there is not so much research yet for all the different shield gases which are offered. So you also see a 6-8. I don't want to talk about this, but because the C6X1 has this lower temperature for its melting pool, it's interesting because it offers you the opportunity perhaps to have higher deposition rates. That's something I'm looking at, and also gives you like more narrow welding seams, welding joints, and higher. So you can speed up in height, but you lose a little bit in width. That's something you have to think about. With this knowledge about all the parameters and characteristics, we can go to the manufacturing process. For the manufacturing process, of course, we need our welding path. And I generate welding paths with something called parametric robot programming. You see it here in the middle in the red box. So again, our column structure. And what we do is we have an ellipsoid cross-section, and our X and Y coordinates are dependent to functions, which are dependent, to the height of our structure. That allows us to adapt coordinates. I will tell you what that means in a little bit after. And it also gives us the opportunity to prevent our printing process from failure. So what you can see, of course, we have different overhang angles. That means we have different layer heights because we're always printing the same material per layer, but it's not always printed vertically where it can spread continuously. And so we have a loss in height for overhang angles, and it's different. It's always changing depending to the value of the overhang angle. And so parametric robot programming gives us a good chance to react and to update coordinates if something works wrong. And that brings us back to our manufacturing process. So we have coordinates which can be updated. We start printing, we have our strategy, and we have a scanning or monitoring method. In our case, it's a tactile measuring method called touch sensing. That's what I was also asking about the depth sensor before, the depth camera. So what we do is every 10th layer, we say we have our surface of our printed structure, and we go for tactile measuring. We have a lot of points we have measured, and then we can say, okay, that is our average structure height, and we can update our coordinates. And all this information combined with weld data and time consumption, everything, it is saved in our rudimentary digital twin. Although this is, or we add some other information, which means we do a 3D scan afterwards, we check for visual failures, we can see from the outside, and then there's also the idea of detecting failures in the inside, for example, with a CT scan, etc. And what we can do with all this information, we know we can do a post-processing if necessary. So if we have, for example, a deflection or overprinted areas, we can remove it, we can overprint it, and we can remove failures. And that gives us a really good tool for the whole process to get our expected result at the end. Why do I call it rudimentary twin, digital twin? That's why it's not, we have no life cycle monitoring. So I would say it stops in my case with the printing because I'm not somebody who can mill the surface, for example. So I'm not really good in post-processing, but I have information till that point. And yeah, it's not completely done over the whole life cycle, for example. But with this knowledge, I would give my first statement to you, which is my PhD should focus on the following aspects: consideration of the influence of the shielding gases, it should include parametric robot programming, so PRP in W.AMCA, because it's not always given. I mean, it's always in the background, but we have for sure to use it because also our technology of the robot is really old and we can just save like, let's say 2000 coordinate points and then it's done. And if you want to print something above 400 layers, 1000 layers, if you talk about columns, that's going to be really difficult. And as a final point, I would like to develop a rudimentary digital twin for our usage or for usage in the construction industry. With this knowledge in our mind, since we have talked about the process W.AMCA itself and hopefully know a little bit how it works, so that we have a tool we can work with for huge structures, we should look for application cases. So construction industry normally means that we have highly individualized buildings. Not only the building itself, the facade, which was already mentioned, and also, for example, columns in the inside. And what I would like to show you on this slide is on the left side, a tree column at the airport of Stuttgart, a V column, how it looks like, on a construction site in Amsterdam. And yeah, I have to tell you a random picture I found in the internet, which shows a knot which color connects column sections with each other. So like rolled sections probably. And yeah, just gives you an impression that we can already highly individualize this structures, but it comes with a lot of effort and money normally. If we take the picture in the middle, I can show you this image of the construction site, which was nearly finished. And what you see is the Y columns again. But if you go one step further into the construction, you see it's also a hidden tree column. And if you just pick one of these columns, you see a lot of challenges for a construction engineer like myself. You have the highly individualized column segments, you have individualized nodes, you have to think about how to connect the segments, how to connect girders at the end, and of course, how to get a connection to the base plate, to the foundation. And so it shows us a high variety and an open research field you can dig in if you think it's a good option for 3D printing. And that brings me to my second statement, also open for discussion, of course, that W.AMCA for additive manufacturing of steel columns itself and the structural and architectural requirements of specific components offer the potential for my PhD. And hopefully you will agree with me at the end of the presentation. If we say, okay, that's an interesting case, I have to tell you that we already decided that a little bit before, even before I started my PhD, because we had a research project on these individualized columns, and especially for architectural application. And what is shown here are 4 different cross sections with different backgrounds while we decided to print these. So on the left side, you can see square cross section with varying width, and it was printed to identify maximum overhang angles. So they are the same for each side, but it wasn't that easy to print them, especially because our orientation of our welding gun was always vertically. That was caused by our robot because we have some trouble with how you call it, how precise it works if you change the orientation of the welding gun. The second one gives us a new challenge because it has an octagon cross section, which is twisted in itself. And that gives us different areas of overhangs. So the maximum overhang angle would be here on the edge while here in the center, it's quite glass. And that leads to an incontinuous layer height. And that was one problem we had to deal with. We were aware before we started printing it, and we had to see how it would progress, if it's a big problem or not. At the end, we could handle it quite well, but of course we didn't have, you can also see it on top, it's not completely flat. But anyway, it worked out. I mean, you can mill it by hand if you want to make it nicer or smoother on the top. No. So for the last two on the right side, they had an ellipsoid cross section. And especially for the one here, number D, it was also to check how can we print these different overhangs again in a continuous print. Beside the overhang angle we were checking for, we also checked how narrow could we print. Actually, it was quite a problem when the density of the coordinates got too close. Then we had our robot struggled a little bit. But yeah, it was okay, I would say. And beside the individualized column sections, we also thought about connecting them. Therefore, that was also part of the research project. We said, okay, how can we connect, for example, standard profiles like square sections or circle sections with each other, and what kind of connection techniques could we use? So they are just shown here, and I wouldn't go too deep into detail. But the last idea was also to connect like printed elements. Yeah, so it's the same idea, and it's just some small challenges we have to solve for that. And by doing this, we printed this example of a steel node here in the middle. It's about 45 centimeters high and has vertical printed areas, but also cantilever printed areas, which is something we deal with at our university for a couple of years now, also with the W.AMCA. I'm not sure if you have heard about it. And yeah, that's how far we get till now. And to tell you the truth, not everything worked fine. So we have still some failures, but it's in the end, if you mill it, it looks nice, I would say. And yeah, here's the second picture. You can see the smoothen layers. It's 3 layers next to each other. We printed in the cantilever direction. And since I'm really ambitious, I was thinking, okay, steel columns, nice, but you can go further. I thought, why don't to transfer this idea to heavy loaded columns as composite columns. So you have a steel core in the middle, and you have a cloak. I'm not sure if you say it for steel as well on the outside, which can be used as a framework as well, which is connected with the steel core multiple times and gives you a highly individualized shape, and of course has all the other benefits of composite columns. And that brings me to my third and last statement, that I would like to transfer the benefits of additive manufactured column structures to composite columns as a final goal and open up new perspective. And that, with all my statements in mind, leads me to a last change of my title of this presentation. I think I have to change it to 3D printing of column structures for structural and architectural applications. And that's how I would like to end my presentation. Thank you for your attention. And here are my statements, and I hope I have given you some base for feedback, as critical as it may be. Thank you very much.
Thank you, Benedikt. Questions from the audience? I think everyone starts getting tired. Question from Philip. Which slide it is? No.
Can you repeat it? I haven't heard anything.
Slide 6.
Slide 6.
Okay, good. While we wait for Philip.
Do you hear me, Benny?
Yeah.
Wait. You want to do the question?
So what's on the x-axis here? That's my.
Now you are both muted.
What's on the x-axis?
On the x-axis, there is just the number of cycles. It's given here on the right side. So we started with 15. We started with 15 cycles for the left parameters, and then so 15 to 35, and here that was the travel speed. But I just wanted to give you an impression. So for example, for both squares, they had all the same information about wire feed speed, about travel speed, the wire electrode, all that stuff was the same, just shielding, the shielding gas was different. And I have a couple of other parameters as well, also for a different diameter, like normally we use 1.2 millimeters. When I used 1 millimeter, like Chris, for example. And yeah, it's just to give you an impression that the distribution of inert gas, I think it's inert gas, and active gas has a huge impact into your welding joint geometry or welding seam geometry. So you are all muted and I can't hear anything.
Just to mute you because you were using the microphone.
All right, perfect. Benny, do you have any hypothesis for what the influence could be here?
For why the layer height is higher?
Yes.
Yeah, that's quite easy. As soon as your melting pool gets, the temperature of your melting pool gets lower, the viscosity of your joint is less, and so it stays higher and less wide. So what happens is, I can use, damn it, sorry.
Well, my follow-up question would be, can you quantify this, or is it a qualitative?
I have data on this, but it's not evaluated. No.
Okay.
So I have a lot. Of course, I have all the measurements of the joint wide as well, and I can probably give you an impression of it, but it's not given in this presentation because it was not what I would wanted to focus on.
Okay. Well, yeah, my recommendation would be the same thing. Like, try to develop this into scaling laws that other people can use, that scale beyond your particular set of parameters, because then it becomes research and, you know, accessible to others. Yeah, but it's thanks for this input, but it's always connected to my special welding device, for example. So it's that's what I'm saying. That's what you have to get rid from. Like, you want to depart from this. You want to generalize it. Yeah, but the problem is all welding device producers have different processes. Okay, so then at least make it scalable for this device, for this manufacturer. So everyone who buys a Fronius device knows how to print already by opening your dissertation. That would be my goal. Okay. All right, thank you. Thank you.
Thank you. Any other question? I mean, no. Just ask you a comment. Of course, you know the MX 3D bridge in Amsterdam?
Yes, sure.
Can you comment in 3 words, 5 words?
What should I comment? How they print it, or how did they print it, or is
Your thought about bridge. What you think about the bridge?
it's impressive because they were the first, but they didn't print it like horizontally. They printed vertically and then welded the single components together. So something I would do for the column structures as well, for example. And they also work with stainless steel. And yeah, it's impressive that they printed it, and they were one of the first. And they have developed from this. That's something you have to say, though. They went further more into the, I wouldn't call it rapid prototype, rapid tooling, but also like building their own boxes with robots and their own software. So it's more into the economic way, making money with it into business.
Okay. Any other question? No. So thank you very much. Thank you.
Thank you, guys.